The last video ended with the ladder problem, and we're going to backtrack a little bit just to review for a second. So if you go back to the first 2 pages in your notes, we're going to take a look at just stepping back a little bit before we step forward. It says we've been taking derivatives with respect to x. What that means is we've had the derivative of 3x squared with respect to x, and we've been saying that that is 6x. An instantaneous rate of change is a derivative with respect to time, so it's d something dt. As time goes by, how is the something changing? Well, we're going to start again backtracking a little bit by translating these sentences into calc. So it says the area of a circle is increasing at a rate of 6 square inches per minute. So if we call the area A, what we'd say for this is dA dt equals the rate that the area is changing as time changes is 6. It's positive 6 because this says increasing, and it'd be inches squared per minute. The volume of a cone, which we'll call V, is decreasing. That indicates a negative rate of change. So we'd say dV dt is equal to negative 2 cubic feet, because volume would be cubic feet per second. So again, this gives you the labels here. This is cubic feet per second. Go try the next one while you wait. All right, so this one we're dealing with the height of a tree, and it's increasing. So we'll call it dH dt equals a positive 1/2. Height would be in feet. Time in this case is in years, so we'd say dH dt is 1/2 of a foot per year. Next step, we're going to write a sentence that could describe the following rates. We can, decide what we want our variable to be, but I'll only do a couple of these. Maybe number 4. Let's say C stands for circumference. Maybe I throw a rock into the lake and it starts to make those concentric circles, and the circumference is increasing. We would say the circumference of a circle is increasing because that's a positive 2. We need the word rate at a rate of 2 inches each day. Done. Let's go look at number 7. Let's say V stands for, this is cubic meters per second, so I was going to say velocity, but that wouldn't be right. So this would have all right, V would stand for volume. So let's say the volume is decreasing because of the negative 10, decreasing at a rate of 10 cubic meters per second. Again, this is just for vocabulary. What are these the formulas for? And then we're going to take the derivative with respect to time. This is a formula for area of a circle. The rate that the area is changing with respect to time would be equal to the rate that pi r squared is changing, obviously because they're equal. So we start by writing it down. We bring the pi out front, and we say this would be pi times, and then we'd have the derivative with respect to time of r squared. Notice we don't have a variable match here, so this is that chain rule. This is like last chapter, dy squared dx was equal to 2y y prime, or 2y dy dx. So what this is going to equal is pi, because it's out front, and I'd have the 2r for the derivative of r squared, but then I'd have to multiply it by the derivative of the guts, which would be dr dt. So this is the formula for the area of a circle, and the rate that an area of a circle is changing is 2 pi r times dr dt. Interesting that it's its circumference times the rate that the radius is changing. Number 9 is the volume of a cylinder. That's what this is a formula for, volume of a cylinder. The rate that the volume is changing with respect to time will be equal to the rate that pi r squared is changing, pi r squared h is changing with respect to time. We pull the constant out front. You don't have to, but it makes it easier to work with. So this would be pi times the derivative of r squared h with respect to time. So what I really need to do is take the derivative of r squared h with respect to time. So we have to be very careful with that because we're going to need the product rule. Let's go ahead and write a little product rule on there. Product rule. And we'll be doing pi times, and then I'll put parentheses. I will do first d second. So I would be doing the derivative of h with respect to time. Don't write h prime. It's r squared times dh dt. That's first d second plus second, which is h, d first. So I would be taking the derivative of r squared, which would be 2r, but there's not a variable match, or the radius is itself changing as time goes by. So it'd be 2r dr dt. And then you could clean that up if you wanted a little bit, but I'm going to leave that because I'm out of space. But in general, so be careful with that product rule. The derivative of r squared with respect to time is 2r times dr dt, not r prime. Don't write that because it's good to know what's changing. And in this scenario, it's not x that's changing, it's t that's changing. Let's go look at the next one. This is the Pythagorean theorem. So when we take the derivative with respect to t of both sides, technically, so we do a squared plus b squared is equal to the derivative with respect to time of c squared. This would be equivalent to, say, maybe you have one car going this way and another car going this way, and this is changing, and so is this changing. They are all changing as time goes by. So, and the latter one was similar to this too. Let's go take the derivative of a squared. Well, it's 2a with respect to a, but for this one, it's 2a times dA dt. And this would be plus 2b times dB dt. And that's going to equal 2c times dc dt. So we get it all cleaned up like that. And then we could actually probably factor out or cancel or divide everything through by 2. So we could actually just say a dA dt plus b dB dt equals c dc dt. A equals s squared is the area of a square, right? So this is area of a square. As the sides change, so does the perimeter change, and so does the area change. So a lot of stuff is related. If I was taking the derivative of the area with respect to time, I'd have to do the derivative of s squared with respect to time. So my rate that the area is changing as time goes by will be equal to twice the side length. If the side length is 5, I'd use a 10. Times the rate that the side is changing, times how fast it's changing. So we would, again, the derivative of s squared is 2s ds dt. Don't use an s prime, please. So 2s ds dt. So hopefully you're getting the hang of how these related rates get derived. Let's go to the next page. This is the formula for surface area of a sphere. It's a function of its radius. So if you had a basketball, the amount of rubber used to make it is 4 pi times the radius squared. As the radius grows, the volume grows, the surface area grows, the density probably shrinks, but we would be taking the derivative of S, that would be the rate that the surface area is changing, will be equal to the rate that 4 pi r squared is changing because they're equal. I always like to grab my constants and bring them out front. So I'm going to do 4 pi times the derivative of just r squared. So I'm going to have 4 pi times the derivative of r to the second power is 2r times dr dt. So the rate that the surface area is changing for a sphere will be equal to 8 pi times the sphere's radius times the rate at which the radius is changing. Next one is the perimeter of a rectangle is twice the length, because I have two lengths, plus twice the width. So this would be giving me the perimeter of a rectangle, So let's start. If I was to figure out how is the perimeter changing, as I change the lengths and the widths, I'd call it dp dt, the rate at which the perimeter is changing, is equal to the rate at which 2L plus 2W is changing. So the derivative of a sum is the sum of the derivatives. So really, this would just be 2 times dl dt plus 2 times dw dt. And I'd be done. You just do them separately. It's a constant multiple. Picture bringing it out front, and I have 2 times dl dt plus the next one would be 2 times dw dt. Or I could even factor out a 2 and say it's 2 times dl dt plus dw dt. All we're doing is practicing taking the derivatives of these equations, so when we start applying them to things, you'll have a better idea of how to derivate them. So this is the volume of a cone, and we're going to have some problems where sand is in a conical pile and it's sliding down. We're going to have cones leaking, and we're going to be taking the derivative with respect to time. On this one, I would be doing the derivative with respect to time of 1/3 pi r squared h. You can probably guess at what I'm going to do. I'm going to grab this constant and pull it out front. And I'm going to have it be, let's call it pi thirds instead of 1/3 pi. I'll have it pi thirds times the derivative with respect to time of r squared h. Right here will be the product rule. So the pi thirds is a constant. Constant multiple rule says stay out front. When I do the product rule, I'll do first function times the derivative of h, which we call dh dt. Don't call it h prime, or I don't know if it's dh dx or dh whatever. So with these real world formulaic problems, make sure you use the formal notation. So that's first d second plus the second function is h, and I'll multiply it by the derivative of r squared, which is 2r times dr dt. And I'm done. The next one is a volume of a cube. Sometimes you'll see E for edge or S for side, but length times width times height. So this is volume of a cube with side S. The rate that the volume is changing over time is equal to the rate that S cubed is changing over time. S cubed's derivative is 3s squared times ds dt. And I'm going to be putting 5 of these on a 5-problem quiz for you tomorrow, just to make sure that you, to make sure people watch the notes for one, and then to make sure they're not just copying them down without the volume on or something. So the next one is circumference of a circle. So we'll take the derivative with respect to time of the circumference will equal the derivative with respect to time of 2 pi r. Guess what I'm going to do? Pull the constant out front, and I'll have 2 pi times dr dt. Had that been r squared, it'd be 2r dr dt, and that's coming next on this one. This is the volume of a sphere. And you can use this first sheet for a while. I'll tell you which ones you need to memorize later, but this is volume of a sphere. Its derivative with respect to time will equal 4/3. I'm going to pull the constant out before I even rewrite it now that I've been doing it a lot. The derivative with respect to time of pi r cubed. Oh, I should have brought the pi out front too, huh? Well, I'll just do that in the next step. So I'll have the 4 pi thirds out front. Usually we just take that whole constant and just throw it out front. And then I'll have the derivative of r cubed. The derivative of r cubed is 3r squared times dr dt. So I guess my last final answer for this will be 4 pi r squared. Oddly enough, that's the circumference, or surface area, sorry, of a sphere. So the rate that the volume's changing is equal to its surface area times the rate that the radius is changing. It's kind of interesting. Next one is area of a rectangle. The derivative of the area will be equal to the derivative with respect to time of the length times the width. This is going to require product rule. It's just not dl dt dw dt. It will be first L derivative of the second, which is dwt. Again, if that was w cubed, it'd be 3w squared dw dt. Plus second, d first. So the rate that the area of a rectangle is changing is its length times the rate that the width is changing plus its width times the rate that the length is changing. Last up, this is the perimeter of a square. You know what? I think I'm going to change this one because we need volume of a cylinder, and I don't remember doing that one. Let me page back a second. I don't think we have volume of a cylinder on here. Oh, we do, so I'm fine. We'll keep that one that we have. That's one of the more important ones we do is the volume of a cylinder one. So let's go back down here. The derivative of p with respect to t will be equal to the derivative with respect to t of 4s. So I'll bring the constant out front, and I will have the derivative of s with respect to time, ds dt. So that's it. That's it for the notes. I think what I'll do is just give like a little mini quiz on these on Tuesday just to make sure the notes got watched. So at the beginning of the hour, there'll probably be a little quiz before you watch some more notes. Have a good one.